Welcome back to this course on Fundamentals of Computer Architecture. In this lesson I will present the CPU performance equation. A computer architect does not have to know many equations by heart. Computer architecture is not rocket science. But there's one equation that every person who calls himself a computer specialist should know: the CPU performance equation. It states that the time taken by a program is given by the number of instructions executed by the program times the average number of cycles per instructions, or CPI, times the time taken by a clock cycle, or the cycle time. Since clock frequency is the reciprocal of the cycle time, this is equal to the number of instructions, which is also called the instruction count, times the CPI divided by the clock frequency. The CPU performance equation directly shows how performance can be improved. We can improve performance by either reducing the instruction count, by reducing the cycles per instructions, the CPI, or by reducing the cycle time, or equivalently increasing the clock frequency. Unfortunately, or what makes computer architecture challenging, these factors, instruction count, CPU, CPI, and clock frequencies, are not independent. In most cases, if we try to improve one factor, another factor gets worse. For example, if we try to reduce the instruction count by increasing the capability and therefore the complexity of instructions, the downside is often that the CPI, or the cycle time, increases. For these reasons, and this is a very important concept in computer architecture, a trade-off needs to be made. That means that we have to try to find the optimal point, where we improve one factor without hurting the other factors too much. We will see many examples of such trade-offs in the lessons to come. Let's look at an example to see how the CPU performance equation can be used to calculate the execution time. We have a program that executes 5 million instructions with the following mix of instruction types. 50% are ALU instructions, which have a CPI of 3. 20% are load instructions, which have a CPI of 5. 10% are store instructions with a CPI of 4. And the remaining 20% instructions are branch instructions with a CPI of 3. Furthermore, our CPU has a frequency of 2 GHz, meaning a cycle time of half a nanosecond or 500 picoseconds. The question now is, what is the execution time of this program on this CPU? To answer this question, we first need to calculate the average CPI. The average CPI is given by this equation here. The sum over all instructions of the frequency of that instruction times its CPI. We can now substitute the values in the table in this equation to obtain the average CPI equals the frequency of ALU instructions, 50% or 0.5, times the CPI of ALU instructions, 3, plus 0.2 times 5, corresponding to the frequency and CPI of load instructions, plus 10% times 4 for stores, and 20% times 3 for branches. This amounts to 3.5. For ease of reference, here is the CPU performance equation again. We can substitute all the information we have in the CPU performance equation to obtain the execution time. The execution time T equals the instruction count, 5 million or 5 times 10 to the power of 6, times the average CPI, which we just calculated and equals 3.5, divided by the clock frequency, which is given by 2 GHz or 2 times 10 to the power of 9. This equals 8 3/4 of a millisecond. Here's another test yourself question, which actually has been taken from the textbook. We ran a benchmark set on our computer and made the following measurements. 25% of all operations executed were floating point operations, and the average CPI of all floating point operations was 4.0, while the average CPI of all other instructions was 1.33. Furthermore, the frequency of the floating point square operation was 2%, and square is a long latency operation with a CPI of 20. Now we have two possible designs, and we need to make a decision between them. In the first design, the CPI of the floating point square operation is decreased to 2.0. In the other design, the average CPI of all floating point operations is decreased to 2.5. Now the question is, which design is best from the performance point of view? My hint for you, use the CPU performance equation. That's it. Thank you for your attention. Oh no, I promised you the solution to an exercise earlier on. Here's the question once more. We want to buy a new computer, and most of the time we use our computer to run two programs, P1 and P2. We execute test runs of our favorite applications on three recent computers, C1, C2 and C3, and obtain the results summarized in this table here. Program P1 takes 1 second on C1, 10 seconds on C2, and 100 seconds on C3. Application P2, on the other hand, takes 100 seconds on C1, 10 on C2, and 1 on C3. Now the question is, when is C1 the best buy? In other words, what should be the execution frequencies of P1 and P2 so that the weighted arithmetic mean is the least, the smallest for C1? Similarly, under which conditions is CPU C2 the best buy, and when is C3 the best buy? Here's again the table with execution time. Now suppose the frequency, or equivalently the weight of P1 is W1. Because there are only two programs, the weight of P2 must be W2 must equal 1 minus W1. Now the weighted arithmetic mean is given of CPU C1 is given by W1 times 1 plus W2 times 100, and that of C2 is given by W1 times 10 plus W2 times 10, and that of CPU3 is given by W1 times 100 plus W2 times 1. Now CPU C1 is better than C2 if its weighted arithmetic mean is less than the weighted mean of C2. In other words, if W1 plus 100 W2 is less than 10 times W1 plus 10 times W2. We can subtract W1 and 10 W2 from both sides to obtain 90 W2 must be less than 9 W1, and we can now substitute 1 minus W2 for W1 to obtain 90 W2 must be less than 9 times 1 minus W2. Now we can add 9 W2 to both sides and obtain 99 W2 must be less than 9. So the weight of W2 must be less than 9 divided by 99, which equals 1 divided by 11, which equals approximately 9.1%. And since W1 equals 1 minus W2, W1 must be larger than 10 times 11, 10 divided by 11, which is approximately 91%. Similarly, it can be calculated when C1 is better than C3 and when C1 is better than C2. So C1 is the best buy when its weighted mean is less than both the weighted mean of C2 as well as C3. I leave that as an exercise for you to do. This completes this lesson. Thanks for watching. In the next lesson, I will present another equation known as Amdahl's law. Hope to see you back.